Redox reactions involve the transfers of electrons between reactants. The substance that loses electrons is oxidized while the one that gains electrons is reduced. Their fundamental and chemistry seen in everything from combustion to cellular respiration. So the first topic will be reported by Junel.
So for our first topic, it's about redox reactions in galvanic cells. Redox reaction in galvanic cells. So here is an example of that. Galvanic cells uses a spontaneous redox reaction to generate an electrical current. So ang redox reaction is divided into two reactions, one occurring at the anode and one at the cathode. So ang anode kay oxidation and the cathode is reduction. Electron flows from the anode where oxidation occurs to the cathode through the external circuit. The flow of electrons generates electric current that can be harnessed. The two cells are connected by the salt bridge, which allows ions to move between the solutions to maintain charge balance. Redox reaction in electrolyte cells, here is an example of that. Electrolyte cells uses an external power source to drive a non-spontaneous redox reaction forward. So the anode is the positive electrode where oxidation occurs, while cathode is the negative electrode where reduction occurs. The electric energy from the power source is converted into chemical energy to drive the desired redox reaction. So ang electrolyte cells nagamit siya for processes like electroplating and purifying metals where the redox reaction would not occur spontaneously. So, in summary, galvanic cells harness the energy from spontaneous redox reaction to generate electricity, while electrolyte cells use electrical energy to drive a non-spontaneous redox reaction for various applications. So the key difference is the direction of electron flow and whether the redox reaction is spontaneous or not. So let's explain the electrochemistry involved in these batteries. So the first one is Leclanche dry cell. The Leclanche dry cell contains a zinc anode, a carbon cathode, and an electrolyte of ammonium chloride and zinc chloride. So the redox reaction involves the oxidation of zinc at the anode and the reduction of the manganese dioxide at the cathode, generating electrical energy. So that is the electric chemistry involved sa Leclanche dry cell. So the second one is Botan batteries. Botan batteries typically use lithium as the anode and manganese dioxide as the cathode, with an electrolyte allowing ion flow. So, ang electrochemistry involved sa Botan batteries kay ang the redox reaction involves the oxidation of lithium at the anode and the reduction of manganese dioxide at the cathode. And lastly, fuel cells. Fuel cells use hydrogen and oxygen as the fuel sources, with an electrolyte allowing the flow of ions between the electrodes. So, ang electrochemistry involved sa fuel cells is the redox reaction involved the oxidation of hydrogen at the anode and the reduction of oxygen at the cathode, producing water as a byproduct. In all these cases, the electrochemistry involves the use of redox reaction to generate or drive electrical energy. The key components are the electrodes, the electrolyte, and the specific redox reaction occurring at the anode, which is ang anode is oxidation, and the cathode, which is ang reduction. So the flow of electron between the electrodes is what generates the electrical current that can be harnessed for various applications. So that's all for the first topic.
Corrosion is essential in electrochemical processes driven by redox reaction. Here's how electrochemical principles explain corrosion. First thing first, anodic reaction. At the site of corrosion anode, metal atoms lose electrons and go into solution as metal ions. This process is known as oxidation. For example, in the case of iron corrosion rusting, the anodic reaction is solid iron undergoes oxidation to solid 2 positive Aq plus 2A negative, followed by the cathodic reaction. Concurrently, somewhere else on the metal surface, a reduction reaction occurs cathode. This reaction involves reduction of species, usually oxygen or hydrogen ions, which gain electrons. For example, in the presence of water and oxygen, the cathodic reaction for iron corrosion is often oxygen gas plus 4AQ plus 4E negative reacts to form water or 2H2O. For the overall corrosion reaction combines the anodic and cathodic reactions. In the case of iron corrosion, it can be represented as Fe solid iron plus oxygen gas plus 4HAQ reacts with to form solid iron 2 positive plus 2H2O or water. This equation illustrates how iron metal reacts with oxygen water to form hydrated iron oxides, commonly known as rust. For the electrolyte, the presence of electrolytes such as moisture from the air or water facilitates the flow of ions between the anodic and cathodic sites, completing the electrochemical circuit. The electrolyte allows for the transfer of metal ions from the anode to the cathode, where they can be reduced, followed by the driving force. Corrosion occurs because the metal tends to revert its more suitable ionic state by losing electrons oxidation when exposed to an electrolyte and oxidizing agent like oxygen. The driving force for corrosion is the difference in electrical potential between the anode and the cathode, which creates an electric current to flow through the metal, accelerating the corrosion process. Lastly, corrosion is fundamentally an electrochemical process where the metal undergoes oxidations at the anode, while the reduction occurs at another location at the metal surface, cathode, leading to the degradation of the metal over time.
Anode versus cathode. Anode is the electrode where oxidation occurs, while the cathode is the electrode where reduction occurs. Conversely, at the anode, which is positively charged, oxidation reactions take place. Anions or negatively charged ions from the electrolyte solution are attracted to the anode. These anions lose electrons at the anode, leading to oxidation and the formation of neutral atoms or molecules. For instance, in the electrolysis of water, hydroxide ions are oxidized to produce oxygen gas at the anode.
Electroplating. Electroplating is a process used to coat a metal object with a thin layer of another metal, typically to enhance its appearance or protect it from corrosion. So maka-enhance siya siyang appearance and makaprotect siya sa mga taya-taya. During the electroplating, the metal object to be plated or the substrate is connected to the negative terminal or cathode of a power source, while a metal plate of the plating material is connected to the positive terminal or anode. Both are immersed in a solution containing ions of the plating metal. When electric current flows through the circuit, metal ions from the plating solution are reduced and deposited onto the surface of the substrate, forming a thin, even coating. Electrorefining. Electrorefining is a process used to purify metals extracted from ores, such as copper, through electrolysis. In the electrorefining of copper, impure copper is used as the anode, while pure copper sheets are used as the cathode. Both are immersed in an electrolyte solution containing copper ions. When electric current is passed through the cell, copper ions from the impure anode are oxidized and dissolved into the electrolyte solution, while pure copper ions are reduced and deposited onto the cathode. The impurities in the anode, such as other metals or metal oxides, either remain in the electrolyte solution or settle as sludge at the bottom of the cell, resulting in the purification of the copper. Chlor-alkali process. The chlor-alkali process is used to produce chlorine gas, hydrogen gas, and sodium hydroxide from a solution of brine or sodium chloride through electrolysis. In this process, a brine solution is electrolyzed using a membrane cell or a mercury cell. In a membrane cell, the anode and cathode compartments are separated by a selectively permeable membrane, while in a mercury cell, a mercury cathode is used. At the anode, Chloride ions are oxidized to form chlorine gas. At cathode, water molecules are reduced to form hydrogen gas and hydroxide ions. Sodium ions migrate through the membrane or electrolyte and combine with hydroxide ions to form sodium hydroxide, which can be collected as a solution. The chlorine gas and hydrogen gas produced can be collected separately for various industrial applications, such as in the production of PVC or polyvinyl chloride for chlorine and in hydrogen fuel cells for hydrogen gas.